This is Lab 3 Part 1. So first thing first, we need to get the flip-flop inputs equations. So we know that JA is B, KA is 1, JB is A0, KB is 1, and DC is B XO with C. So once we get equation, we can complete the truth table here and draw the state diagram accordingly. So the sequence will go from 0, 0, 0 to 0, 1, 0 to 1, 0, 1 to 1, 0, 0 to 1, 1, 0 to 0, 0, 1 and back to 0, 0, 0. So this 0, 1, 1 and 1, 1, 1 here is the transient state. And now we move to the circuit. So first we set the clock to 1 Hertz. And this clock here it will read the input when it is rising edge. So when I press, the clock will change from 0 to 1, and that's the time it read the inputs and show the output at the LED module. And so as you can see here, the sequence will goes from 0, 0 to 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1 and back to 0, 0, 0. And this will keep on looping unless we force a certain value to allow the transient state here to be checked. So if we want to check 0, 1, 1, we need to look for the 1, 1, 0. So from this 1, 1, 0, if we change the KB to 0, the next state will change accordingly to 0, 1, 1. Hence, check. So likewise, we can do the same thing to 1, 1, 1 if we want to check 1, 1, 1. Thank you. Continue to the previous part, transient state. So like I mentioned it before, there are two transient states, 0, 1, 1 and 1, 1, 1. So if we give them a particular value, either 1 or 0, we can allow the transient state to be checked. So this is the 1, 1, 1 and 0, 1, 1 transient state here. So if we give KB equal to 0, 0, 1, 1 will go to 1, 1, 0. 0, 1, 1 go to 1, 1, 0. So same thing like the 1, 1, 1 to 0, 0, 0, 1, 1, 1 to 0, 0, 0. 1, 1, 1 to 0, 0, 0.
I am using the output reverse light tracer, and this our output is start from 0, 1, 1, 1, 1, 1, 1, and later again it will start from 1, 0, 1, 1, 1, 1, 1, 1. And from this is our output. We set the count MR, CP, CT, PE to high, and our CP is connected to switch. And because we want to control it, and we will stop at 1, 0, 1, 1, 1, 1. Okay. And the output is going to depend on the input. When input is 0, 0, 0, the beginning of the output will become 0, and another will be 1. And for the second one, when the first input is 1, 0, 0, and the output will be 1, 0, 1, 1, 1, 1, 1, 1, and later, and this is our circuit.
Hi, this is part 2 of lab 3 for the reverse light chaser, and here just to explain why Q3 is not used here. So actually this binary counter is a 4-bit binary counter, whereas the decoder is a 3-bit decoder, so there can only be 3 inputs for the decoder. So we decided to use these 3 inputs because Q3 is actually the most significant bit. So for example, when it's 1, 0, 0, 0, it's the same as it being 0, 0, 0, 0. So when it becomes 1, 0, 0, 0, it's just like the numbers looping again. So from let's say 1, 1, 1, 0, 1, 1, 1, it goes to 1, 0, 0, 0. So it's like it loops back from 1, 1, 1 to 0, 0, 0. So that's basically why we do not use Q3, because it's considered as a don't care in this case. This is part 2 of our lab 3, and we're doing the last part of this part, which is the decoder. So from this statement, the max terms, we got this truth table. So when the ABC is 0, 1, 0, it has to be 1, 1, 0, 0, it has to be 1, and 1, 0, 1, it has to be 1 as well. The rest is 0. So we used the decoder to do this, and we connected A, B, and C to A0, A1, and A2. So and they are connected to switches so that we can control the input value. So as you can see from the data sheet, this is the data sheet, and to get the answer of 1 when these values are in, we used a triple input NAND gate which is connected to Y1, Y2, and Y5. There's a reason why we chose 1, 2, and 5 is because for when the inputs is 1, 0, 0, it has to be 1, right? So when it's 1, 0, 0, Y1 equals to low. So if we connect it to a NAND gate, when one of the values is 0, the rest is 1, it will be inverted to the value of 1. So for example, let's say high, high, low, which according to the truth table is 0. So high, high, low, when it's high, high, low, Y1 is high, Y2 is also high, Y5 is also high. So that will result in 1, 1, 1, and it will flip over and become 0. So it will not light up. So likewise, when it's low, high, low, 0, 1, 0, it has to be high as well. So Y1 is high, but Y2 is low, and Y5 is high. So it will result in 1 because of the NAND gate here. And now we will demonstrate it using the circuit here. So the first switch is connected to A0. The second switch is connected to A1, and the third switch to A2. So when it's, let's say, 0, 0, 0, it doesn't light up. When it's 0, 0, 1, it doesn't light up as well. But now let's try 0, 1, 0, 1, 0, 0, 1, 0, it lights up. And let's try another one, 1, 0, 0, 1, 0, 0, it lights up as well. And let's try another one just to check, 1, 1, 0, it's actually supposed to be 0, so 1, 1, 0, first switch and second switch, it will be off. And the last one, 1, 0, 1, 1, 0, 1, it lights up as well. And that's all for this part. Thank you. So here is lab 3, and we're doing part 3 for now, and we're supposed to construct this circuit, and our circuit is over here. You can see we're supposed to use an inverter here, but we do not have an inverter. That's why we use a series of 3 NOR gates as an inverter, and that is also to exaggerate the delay, which is written here. So this is the NOR gates that we use, and these are the series of 3 NAND gates that is used to complete the circuit. So according to our truth table, the hazard might occur here, static 1 hazard might occur here because it's not covered. So this may occur when it transitions from 111 to 101. So, and for this lab, we're discerning only the input of B, because the only difference here, 111 and 101, is the input B, and which is connected to our clock. And as you can see from the oscilloscope here, there is a delay here. When 111, this is the input B, so it's 111 goes to 101 here. It's supposed to remain as 1 according to the truth table, but due to the delay and the static 1 hazard, there is a slight delay here. And now I'll zoom it in so that you can check it. And as you can see, when it's 1 to 0, there's a slight dip here, and the slight dip, the difference, the delay here is approximately 60 nanoseconds according to the oscilloscope. But however, this can be overcome by using a cover, which will be shown later. Okay, so now we have implemented the cover. As you can see here, we implemented the cover here to cover it up, which is AC in the SOP, and we have the SOP, the new SOP here, and we convert it to what according to our circuit, which is made out of NAND gates. So it's supposed to be something like this. And since A and C will remain as 1, we just connect A and C to VCC, which is 1. And this is the circuit, you can have a look. And after implementing the cover,
we got this result on the oscilloscope, and you can see here that there's no delay at all when the input for the yellow line is the input. When the input is 1, and even if it's 0 and it goes to 0, it still remains as 1. So the cover successfully stopped the delay and made the value remain as 1 as it's supposed to be. Okay, thank you.